Why do real components complicate Ohm's law? Imagine trying to follow a simple recipe and finding out that one ingredient keeps changing its amount every time you look away. That's kind of what happens with real electrical components and Ohm's law. Ohm's law states that the voltage across a resistor equals the current flowing through it times its resistance. It's a straightforward rule for ideal resistors, which are perfect and unchanging. But real components are more like unpredictable ingredients. They don't always follow that simple rule. First, many real components like diodes, transistors, and thyristors are non-ohmic devices. Their voltage-current relationship isn't a straight line. For example, a diode only allows current to flow in one direction and needs a certain minimum voltage, called the forward voltage, before it conducts. Before that point, almost no current flows. This means the current doesn't increase proportionally with voltage, breaking the simple V equals R rule. Next, temperature plays a big role. When current flows through a resistor, it heats up. Metals tend to have higher resistance as they get hotter. So, resistance isn't fixed, it changes with temperature. If you're designing a circuit, you can't just assume resistance stays the same because the heat generated by current can make it fluctuate. This makes the relationship between voltage and current more complex than the basic law suggests. Material and construction also matter. Ohm's law works best with metallic conductors under stable conditions. But many components like semiconductors have complex conduction mechanisms that don't follow the simple linear rule. Plus, the physical design of components can introduce parasitic effects like inductance and capacitance. These effects cause current and voltage to behave differently at different frequencies, which Ohm's law doesn't account for. Some components also behave differently depending on the voltage's polarity or over time. Capacitors and inductors store and releases energy, causing the voltage and current to change dynamically. This makes the simple V equals R equation insufficient because it doesn't include energy storage or time-dependent effects. In real-world electrical engineering, these factors mean Ohm's law is a good starting point but not the whole story. Engineers use it to analyze circuits, but they also need to consider how components behave under different conditions. For example, when designing circuits with light-emitting diodes, Ohm's law helps determine the current-limiting resistor, but engineers must also account for the diode's forward voltage and how temperature affects it. So, real components complicate Ohm's law because their resistance isn't always constant or linear. Their behavior depends on temperature, voltage polarity, material properties, and energy storage effects. That's why engineers need more detailed models and careful analysis beyond the simple V equals R rule to make sure circuits work reliably.